Sorry for the delay. Welcome to the CERIAS Security Seminar. Today it's my pleasure to introduce Ke-Shin Pei. Ke-Shin is a graduate student in the Computer Science Department at Purdue University. His research interests include data mining and security, especially on solving security problems using both program analysis and machine learning techniques.
Good afternoon, everyone. My name is Ke-Shin Pei. Thank you for attending this talk. Today I will present our paper LEAPS, Detecting Camouflaged Attacks with Statistical Learning Guided by Program Analysis. This is the joint work with Zhongshu Gu, Qifan Wang, Professor Luo Si, Professor Xiangyu Zhang, and Professor Dongyan Xu. So today, enterprise infrastructures are facing more severe cyber threats powered by sophisticated attack techniques. Usually, the cyber attack can be divided into two stages. In the first stage, the malicious adversary will try to intrude in the enterprise network. They can do this either by exploiting system vulnerabilities or leveraging some social engineering techniques to trick the innocent users to perform harmful operations unintentionally. Then they will implant their persistent malicious backdoors and payloads into some victim machines. In the second stage, the hacker will infiltrate into the network again and connect to the backdoors that they implant in the first stage. Then they could send the command and control to the malicious payload and control the victim systems to achieve their goals, such as stealing sensitive information from the machine, infect other systems, or make the compromised machine one of the attacker's bot to conduct DDoS, distributed denial of service attack. Malicious adversaries always strive to make their attacks to be more stealthy and leave fewer footprints in the system that they attack. Typically, they try to implant the malicious payload under the cover of some benign or normal applications in order to evade the detection of system users. We name such attacks as camouflaged attacks. Camouflaged attacks can be divided into two types. The first type is the offline attack. Adversary embed the malicious logic within the binary of a legitimate application and can use some phishing technique to trick the user to download and install it. The malicious logic can run in parallel with benign logic. The second type is online attack. Adversary can choose one running process that is vulnerable and inject the malicious logic directly into the application's memory space. Then they redirect some program path within the benign logic and execute the malicious payload within the same process context. Actually, today, camouflaged attacks pose some difficulties for traditional attack detection approaches because the recorded malicious and benign behaviors are mixed together. Such noise in the dataset may greatly affect the accuracy of distinguishing malicious behavior from benign behavior for future detection. Generally, attack detection approaches in the literature can be classified into two categories: program analysis based and statistical learning based. Both have their pros and cons. For program analysis approaches, it can generate a precise execution model, but this is usually built upon heavyweight instrumentation on the program. Furthermore, if the training data is not complete, it may perform bad on the unseen testing data. For statistical learning, the advantage is that it is robust on dealing with unseen testing data. But in order to generate such model, it needs domain knowledge to process the raw data to make it understandable by learning approach, which is non-trivial in most of the learning process. Furthermore, the performance of statistical learning approach is closely related to the quality of the training data. For example, when facing the noisy dataset generated by the camouflaged attacks, it may derive an inaccurate model. Let's explain what is exact the problem that will be introduced by the noisy dataset. In the first stage, we could obtain the pure benign dataset to provide positive training samples. And then we could also obtain the dataset contains camouflaged attacks as the negative training samples. But because such negative training data contains both benign and malicious events in it, which is denoted in the picture, the positive sign is for the benign data sample and the negative sign is for the malicious data sample. So finally, we will get a misleading decision boundary that biased towards the positive side. This decision boundary may misclassify benign testing data as malicious in the future. The intuitive solution to solve this problem is minimize the influence of benign data points within the negative data sets. Thus, we can derive a correct decision boundary to actually accurately classify the testing data. In order to address the noisy dataset problem, we develop a new statistical learning-based attack detection system called LEAPS, which stands for Learning Enhanced with Analysis of Program Support. LEAPS is inspired by a recent proposed vision of learn to reason, which promotes mutual enhancement between statistical learning and formal analysis reasoning. LEAPS integrate the capabilities from both program analysis and statistical learning camps. To be more specific, we leverage program analysis technique to refine the statistical learning model, and finally, we can boost the detection accuracy of learning approach for such camouflaged attacks. Through our investigation on the behavior of camouflaged attacks, we find that usually benign and malicious programs cluster separately in their code regions that are mapped in the memory. We give a concrete example here. The above one is control flow graph of a benign Vim editor, and the below one is control flow graph of a Vim editor that contains a malicious backdoor. After comparing these two control flow graphs by aligning the loads with same address, we find that benign subgraphs of these two control graphs are very similar to each other. On the contrary, the malicious subgraph in the second control flow graph is quite independent and isolated from other program paths. The root cause is that parasitic malicious functionality is by nature not related to its host application's functionality. Thus, we think that the code distance to the benign subgraph is a good measurement for the benignity of the code. Then we'll talk about the key idea of LEAPS. We use the system event log and transform it into the training dataset that is understandable by learning model. We also derive the control flow graph information from the system event log. One only has benign events and the other one contains camouflaged attack. By comparing these two control flow graphs, we assign corresponding weight for each data point in the negative dataset. This weight is based on the distance of code address to the benign control flow graph. So with such weights in the dataset, we train a weighted SVM model for classification on future data. So this is the overview of the system design. In the system of leaps, we have 4 major modules: the stack partition module, data pre-processing module, control flow graph inference module, and supervised learning module. The input is the system event log. It contains the recorded system events and their corresponding stack work trace. Through the stack partition module, we partition each stack work trace into 2 parts: the system stack trace and application stack trace. The system stack trace is the stack trace at the system layer, contains system-level behavior of the program. For example, the shared library and the kernel information. We use such system-level behavior as our training and testing to distinguish benign and malicious behavior. The application stack trace is the stack trace within the application layer. The application level program execution information is embedded inside the application stack trace. Through data pre-processing module, we transform the log into the dataset that can be used by the supervised learning module. As we mentioned, the negative dataset is noisy because it contains both benign and malicious data. So through the control flow graph inference module, we derive the control flow graph from the application stack trace and assess the weight by comparing the control flow graph. Finally, by assigning the weight to the training dataset, we build a weighted SVM model. This is the overview and the workflow of our system. And then, after discussing the overview, let's inspect the details for the functionality of each module. Data pre-processing is the essential step before applying any learning model. It requires the domain knowledge to extract the features from the raw data and discretize the data to make it adaptable to the learning model. We extract 3 features for each event: the event type, the library set, and the function set. For each event, it has one-to-one mapping to the event type. But for each library set and function set, there are a sequence of library call and function call in the call stack. So we need to further abstract this call set sequence to a single value for each event, which can be transformed as the input to the learning model. Hence, we leverage the hierarchical clustering, which is an unsupervised learning algorithm, to group similar library function sets into one cluster and assign that cluster number to the corresponding library cluster number and function cluster number. We use the pairwise set dissimilarity as the measurements for distance, and then apply the hierarchical clustering. Then we'll talk a little about the control flow graph inference module. As we know, traditionally people use system event log for performance debugging. At the same time, program execution information is also embedded implicitly within the log. So the functionality of this module is to infer the control flow graph from the system event log. In the previous slides, as I mentioned, we leverage the system stack trace to generate the dataset for training and testing. Here, we mainly leverage the application stack trace attached to each event to infer the control flow graph. As the event is predefined when triggered logging, the call stack trace may not be complete, which may not include each instructions and the basic block for the control flow graph. But it is fine to reflect the general execution structure of the program. Here we give an example for control flow graph inference. Assume we have 2 adjacent events, event 1 and event 2, in the log, and both of them has their own application stack trace. The first program path we can infer from the log is the function invocation relation embedded on the stack. We call it explicit path. And then we also find that the first 3 addresses and on the stack are the same and they branch at the 4th address. Then we can infer that there exists some implicit path from address 4 to address 6 in this case. So based on this information, we derive the control flow graph from the system event log, which is incomplete as I mentioned. We derive a benign control flow graph from the benign log, which is used for weight assignment for positive training data, and derive a mixed control flow graph from the noisy mixed log, which is used for weight assignment for negative training data. We assign the weight for the negative data set based on the 2 criteria. The first one is the program path that is close to benign control flow graph is more likely to be benign. And the second one is program path that is far away from the benign control flow graph is more likely belonging to the implanted malicious payload. We compare these 2 control flow graphs edge by edge. For the edges that appear in the benign control flow graph, we assign 1 to its weight. For the edges that do not appear in the benign control flow graph, but close to the benign nodes, we assess their weight based on their distance to their adjacent nodes. For edges that are totally far away from the benign nodes, we assign 0 as its weight. With weight for each edges, we calculate the weight for each corresponding event and assign the weight to the negative training data. So the final step is to learn an accurate binary classifier from the training data. We use the support vector machine as our classification model. This is the formulation of the original SVM with soft margin. We revise the formula and introduce the weight of each data point in the training data into the formula and build a weighted SVM model. Then let me talk about the implementation of our system. For the system event logging, we use the ETW, which stands for Windows Event Tracing for Windows framework. It's a general purpose tracing engine introduced since Windows 2000. It can trace the system event across layers from user space applications to kernel components. In our stack trace partition module, they refer to the application stack trace, which is for control flow graph inference, and system stack trace for training and testing. It can also enable stack working on each predefined system events. For the statistical learning part, we leverage the SciPy for hierarchical clustering and libSVM to build our weighted support vector machine. We test our experiment on 21 camouflaged attack samples. There are the combination of 5 different host applications, including such as Chrome, Firefox, Notepad++, and 3 different malicious payloads and 3 different attack methods. As the accuracy itself is always not enough to measure effectiveness of the detection model, we use 5 different measurements. ACC is the abbreviation of accuracy. It measures the portion of the true results, both the true positive and true negative in the total test samples. PPV refers to positive predictive value, also known as precision. PPV measures the portion of actual benign samples in all predicted benign samples. TPR is true positive rate, also known as recall, which measures the number of instances that are correctly classified as benign out of the total real benign instances. Similarly, TNR refers to true negative rate. It is also known as specificity. Similar to TPR, TNR calculates out of the instances that are actually malicious the number of instances that are correctly classified as malicious. NPV is negative predictive value. Similar to PPV, NPV measures the portion of the actually malicious samples out of the total predicted malicious samples. For each case, in 21 test cases, it consists of 3 data sets. The pure benign data set contains no attacks and is used as positive samples for our training. The mixed data set contains the camouflaged attacks, and it also logs the host applications data. The pure malicious data set only contains the malicious payload's behavior. We obtain this by manually extract and compile the malicious payload. So this data set is only used as a ground truth for testing. In the training phase of our model, for the positive samples, we randomly select them from 50% pure benign dataset. For the negative samples, we randomly select from mixed dataset. In the testing phase, we test the positive samples randomly select from the rest of 50% pure benign dataset. And for negative samples, we randomly select from the pure malicious dataset. We compare our results with both the original support vector machine model and system-level core graph model. We find that our weighted SVM model outperforms both SVM and core graph model in all test cases on all 5 measurements. This is the evaluation result, which contains 30 offline infection cases. The x-axis denotes the 5 different measurements, and the y-axis denotes the actual value of each measurement. The red bar is our weighted SVM model. The green bar is the original SVM model, while the blue bar is the core graph-based detection model. This is the detection result comparison for online injection detection. We can see the constant outperformance throughout the 21 cases. Here, let me give a case study from our evaluation. In this case, the host application is WinSCP, and the malicious payload is a reverse TCP shell. We leverage the tools on the Metasploit framework to perform this attack. We use the MSF payload to generate interpreter payload. This payload used the reverse TCP as the connection for command and control. It can perform keylogging, file uploading, taking screenshot, and collecting password hash on the victim machine and crack it offline. Then we use the MSF encode to encode the payload and embed it into a WinSCP binary. For the detection accuracy, we see it using core graph. The rate is around 75% detection rate. And for original SVM, it is around 86%. If we use weighted SVM in leaps, we can boost the accuracy to 93%. For more results, you can refer to our paper. Here we discuss some limitation of our system and what we want to explore in the future. Assume that the adversary can add the payload source code into the code base of the benign application. Currently, LIPS is not able to detect such attacks because all the benign code address will shift. If you remember, in our control flow graph inference, one assumption is that the benign and the camouflage attacks share some address for the benign execution path. So we need to revise the control flow graph comparison algorithm. We should not only consider the code address distance, but also consider the shape of the control flow graph, which may use the structured learning, which is a hot topic in machine learning community. Currently, we only consider the order of adjacent events, but they may exist some causal relations between multiple events that are far away from each other in the log. So we need to explore more learning approaches to review the hidden connections between them. One possibility may be the hidden Markov model. So this is the conclusion for our paper. We target the camouflaged attacks that run the malicious payload under the cover of some benign applications. Such attacks can mislead the statistical learning approaches to generate a round decision boundary. LIPS integrates capabilities from program analysis to improve the results of statistical learning. From the evaluation, we see that LIPS can effectively outperform classification accuracy of traditional learning models on camouflaged attacks. Thank you for your listening. Any questions? Yeah.
When you showed us the when you showed us the data flow, you said that you analyzed the code section of the malware.
Yeah.
What do you do with the code that is hidden within the data section? Do you find that, or do you look into it?
Do you mean? Do you mean this
Yes.
control flow graph?
Yeah. When you create the data flow, you said you go into the code space to find the flow of the program.
Yeah.
By analyzing some other malwares, you have
Mhm.
some of them hide some functionalities and other flows within the data section.
Yeah. I understand.
So do you take that into consideration, or will it be considered part of malware?
Actually, this we compare this malware with actually the malware is a children application. The application is benign in itself, and we always run two runs. The first one is the benign runs, and the second one we use the same machine and run the children application just after the benign one runs. So we can gain the address space of, we can see that there are some sharing of the address space from these two runs. And the remaining address in the second run, which contains the malicious payload, may have some address that have not been seen in the previous run, which is the benign application.
Okay. Another question I would have: how would you deal with rats, remote access trojans, and the third one would be time constraint attacks? I mean, some people will write malwares to run in a specific time. So if you're testing it against your application and that time is not there, you'll not know that there is an extra execution or an extra function hidden somewhere.
Yeah. That's one of the limitations of our work. And currently we're working on the spatial temporally dispersed log entries from very far away and a different lightweight log. And we are currently working on that. That is one of the limitations in LIPS, actually. Thank you.
Thanks.
Any other questions? If no, thank you so much. Okay.